Okay, a farmer has 6,000 meters of fencing and wants to create a rectangular field subdivided into 4 congruent adjacent plots of land. Determine the dimensions of the field if the area to be enclosed is a maximum. Okay, so we want to create a rectangular field. So let's say that this is a rectangular field, and we basically want 4 congruent adjacent plots of land, right? So because it's subdivided, we're going to add fencing here. Determine the dimensions of the field that the area is to be enclosed that is a maximum, right? So we can understand that if we're looking at fencing, we're looking at the perimeter, right? So I can understand that this is going to be my length. I'm going to let L represent length, and I'm going to let W represent width, and let's do length in meters and width in meters. Okay, so let's do all of these are widths. Okay, and we can understand that the total perimeter here can be explained by the expression or the equation 5W plus 2L, right? And this is what the perimeter is going to be. Now we know that the perimeter here is basically 6,000 meters, so 5W plus 2L is equal to 6,000. Okay. We also know that the area here is length times width. Now the only issue with this is that we actually have 2 variables in our function, right? In the case of the area function, which we're trying to maximize, we actually have 3 variables. So you want to make sure that you have a dependent variable and an independent variable. You can't have 2 independent variables, right? So in order to do that, I need to substitute one of the variables as a representation of the other, right? So what I'm going to do here is, using my first equation, I'm going to substitute for, let's do L, right? So for 2L, I'm going to isolate for L, and I'm going to move the 5W to the other side, so you get 6,000 minus 5W. Then L here is equal to 3,000 minus 5W if I divide over 2. If I divide all of these by 2, right? So I divide this by 2 and this by 2, right? So this is what L is equal to, right? And now what I want to do here is I want to make the area function just a function of one of the variables. So I'm going to do this with W. So I'm going to substitute this into, into my area function, excuse me. And if I substitute this into my area function, area is equal to, wherever you see L, I'm going to plug in 3,000 minus 5W over 2 times W. And in this case, the area is now a function of W. So A of W is equal to 3,000 W minus 5W squared over 2, right? And now what you can do, if you want to clean this up, this is, if you divide all of these terms by 2, this is 1,500W minus 5 over 2W squared. Okay, so now that we have that, we actually have a function with 2 variables. We want to find the dimensions if the area is going to be maximum. So to optimize our area, I'm going to find the first derivative and let it equal to 0. So the first derivative of this function here is 1,500 minus 5W, right? And if I let a prime of W equal 0, then 1,500 minus 5W is equal to 0. I'm just going to move this here, but negative 5W is equal to negative 1,500, right? Because I'm moving this guy to the other side. And then if I want to solve for W, W is negative 1,500 divided by negative 5. The negatives cancel out. W is equal to 300. Okay, so if W is equal to 300, that's our width. If you want to solve for our length, you can substitute this into equation 1, right? So if I substitute this into equation 1, then 5 times 300 plus 2L is equal to 6,000, right? 2L plus 1,500 is equal to 6,000. 2L is equal to 6,000 minus 1,500, which is basically 3,500, right? And sorry, 4,500. It's 4,500. And as a result, L, if you divide by 2, L is basically equal to, I'm just going to move that there. Okay, so L is basically equal to 4,500 divided by 2, which is 2,250 meters. Okay, so therefore the dimensions, let's use a darker color here. So therefore, the dimensions of the field will have a length of 2,250 meters and a width of 300 meters. Okay, and that's how you can optimize